Good afternoon. I'm Luc Dekoninck from the University of Ghent, and I'm an environmental noise specialist, and I'll give a talk about detecting and correlating aircraft noise events below ambient noise levels using open sky tracking data. The context is the European Environmental Noise Directive. It includes a standardized noise mapping, but those noise maps are limited to an LDEN contour of 55. There is also an ISO standard for airport noise monitoring. But the problem is, noise annoyance is detected well outside the range of those standard noise maps. And aircraft noise is acknowledged as an important health burden. In the most recent report of the WHO EU section in 2018, they detect health impacts from 45 dB LDEN and 40 dB L-night. The WHO also recommends to shift to indicators that are sensitive to event counts. But there's not enough scientific evidence at this moment to go along this path at this very moment. So the goal is to quantify event-based noise exposure and later on the health impacts at longer distances from the airports. This is the WHO noise recommendation for aircraft noise, where you see the 45 LDN limit and the 40 dB L-night. There is strong evidence, epidemiological evidence for that. So most of you are not in the noise business, so I will give you a short course in noise before we can continue. So measurements are typically performed in LAEQ, which is a measure sensitive to the sensitivity of the human ear. We call it A-weighted, and the typical resolution is 1 second. Those noise measurements are aggregated over time acoustically, and we conserve the acoustic energy over time, and then we call it an LAQ for a certain period. Noise events are identified by an LE-max. They have an event duration, and we also have a property we call the SEL, sound exposure level. That's actually the total acoustical energy in the event, but compressed as if the event only had a duration of 1 second. In the curve here next by, you see the dynamic nature of a noise sequence, and the red line is then the acoustical energy averaged over that period. The LDEN, I already mentioned, is a weighted average of 3 episodes a day, evening and night, and the day is counted as such without the penalty. In the evening we count 5 dB extra for the potential effect of higher annoyance during that episode, and there's a penalization of 10 dB for the L-night. So that's how we calculate LDEN. Exposure modeling is based on 3 sets of data. We typically use a flight database delivered by the airport and the radar data, and we refer to what we call the aircraft noise and performance database. An emission model is provided in that methodology and provides an LE-max, an SEL per aircraft type for the different engines. It's sensitive to operations, the actions, the load of the airplane, and so on. And the noise map becomes then the sum of all those SELs divided by the time in that evaluated time window. And those calculations are available in commercial and non-commercial applications. But that emission model is only valid for aircrafts up to 25,000 feet, and it's only typically applied in the vicinity of airports. So we will need an extension of that model if we want to detect the impact of cruising aircrafts. The standard noise monitoring is organized within an ISO standard that provides the specifications for the noise monitoring near airports. And an event is defined as an occurrence that goes more than 10 dB above the ambient noise levels. And the event duration is calculated on the window that event is about 10 dB above the maximum level. So that's the definition of an event in that standard. Here as well, you can only detect events if they are at least 10 to 15 dB above the ambient levels. And what I want to do is to detect events at lower levels, so we will need an extension to that ISO standard as well. Of course, that data is only available if you have a project with that airport. So the idea is that in the end, we want to switch to an open system that predicts noise events at any dwelling for any time window. And there the ADS-B records can act as the flight data and the radar data in the calculations. That's how I ended up with Open Sky Network, and I thank you already for the access to that data. We need to extend an emission model to predict real-life exposure. So we will have to detect those low event exposure events and model the real-time exposure, including meteorological effects and the potential masking of ambient levels later on. So in this publication, we only address the first component, detect and identify aircrafts. So the challenges in long-distance monitoring, well, sound travels at a little bit slower than light speed. So the speed of sound is 340 meters per second. If an aircraft is cruising at an altitude of about 10 kilometers, it takes about 30 seconds before that sound hits the receiver on the ground. In that time, at a speed of 400 knots, the plane has traveled about 6 kilometers. But that's not the whole story. Aircraft has also a directivity pattern, which means that the sound is emitted more to the back of the plane than, it's not a point source in our technical terms, but the largest amount of sound goes by the rear, due to the engines, of course. So which means that the maximum level is somewhat later on even in that event, just not the closest point from the aircraft to the receiver, but it's a combination of that effect of directivity and the increased distance over that period of time. So that again can give you about 60 to 90 seconds delay before you actually hit the maximum level of the aircraft passage. And then it's moved another 10, 12, 15 kilometers further on. So, and of course, we want to do this for all variations in ambient levels, even if it would not go more than 10 dB above the background exposure. We, in the end, reach event durations of 2 to 3 minutes. The solution for this whole challenge is to use spectral noise measurements. So, first, I use any available data series I collected for any other purpose. And I can use the data since January 2016, when the Open Sky Network started to collect data at large. I have various locations with measurements at high and low exposure conditions for aircraft noise and high and low exposure conditions for other sources, mainly traffic noise and industrial sites. And the goal is, of course, collect events to model the exposure in the future. This is a typical normal event. It's about 15 dB above ambient level. The black line is the ambient level. And the red line is my event detector, which is the sum of the low frequency components between 40 and 250 Hertz. And in this event, the low frequency component emerges about 23 dB, while the total noise level only increases 15. This is how that information looks like in a spectrogram. This is a low noise event. Background exposure is about 40-42 dB. And you see that's quite dynamic. But there is a low frequency event that gives you about 2 dB in the total noise level, but 18 dB in the low frequency detector value. This is the aircraft in the spectrogram. The other stuff are probably the dog of the neighbors in the mid frequencies, and the high frequency events or birds. If you wonder if you would notice this event if you're outside, you will definitely. It's really dominant in your noise environment, although it doesn't grows highly above the ambient levels. So this is an example of background levels about 48 dB, and you see two events close together who barely affect the total noise level, but they have a detector value of plus 18 in the low frequencies. Those are the two events seen in a spectrogram. Of course, we can have colliding events. This is a case where there are actually 3 aircrafts colliding in the sound that is measured. This is a spectacular one. That's a propeller aircraft, the Antonov. It's tonal noise. That's much more annoying compared to broadband noise. And this is how the spectrum looks like. And this is, oops. This is an illustration of the Doppler effect. So the tonal component changes its frequency due to the relative speed of the aircraft towards the receiver. So next step is identifying the source. So many aircrafts in the sky means we have to calculate some stuff to identify the aircraft. We have the event window in the measurements. So at that point we calculated 3D distance to every aircraft in that vicinity at that moment. We also calculate the sound travel time and the sound arrival time at the receiver. And if the sound arrives within the event window, then we have a match. So at that moment you can start to calculate all the stuff you want from that noise event and use that to feed the prediction model. So this is the Antonov again. The grid at the right side shows 2 tracks of 2 different airplanes. One grid cell is 10 by 10 kilometer. The red dot is the receiver position. And that aircraft passed by at a horizontal distance of 16 kilometer. Distance to source in 3D was 17 kilometer. Aircraft was flying at 6,600 meters and at a ground speed of 256 kilometers per hour. The event duration is about 3.5 minutes. It was early morning and yeah, it's quite noticeable. In busy skies, here you see the event detector is set to 40 and you see 3 events, only one is triggered by that event detection. And you have about 10-15 potential flights and link with the window itself with travel time. If you include the travel time and the arrival time of the sounds, then you end up with that specific flight, Ryanair, Airbus, I think, was it? So, with a lower detection limit, the tree could be separated, and then we have a solution for each of those peaks. This is the example with the three colliding events. There you see about 6, 7 different tracks, and 3 of them fit with these parts in the event window. That's a type of event we will not use in the model, of course. That's part of the automated procedure to decide if we can use the detected event or not. So, to do is we have to remove false positives. You might have seen something that matches an event, but the noise measurement is not an aircraft event, something that has to be done. We also have to remove the disturbed events, and we have to also calculate a sound exposure level, including the higher spectral components, but keep the component of the sound that disturbed the event out of the equation. When in doubt, we'll remove the event from the collection, so we don't add bad data to the modeled set. So we will have to classify the aircrafts, and we will link that to the noise classifications according to the ANP database. This will be a severe exercise, but that's already working quite well. We will have to include other parameters affecting exposure. We have to check if the event happened up or downwind, and we have to quantify the impact of the directivity on the noise emission. And of course, the next step is create predictions and applications. 2 types of applications: time series at fixed locations and maps. So this is a test with 1 day of OpenSky data, where I used the standard model without adjusting for the fact that it is not valid for higher altitudes. So just showing how it would look in the future. There is also a survey added, so the green area is the standard noise map, and then you see the bigger dots are reports of annoyance due to aircraft noise, so well outside that LTEN contour. And that's of course the purpose of this work, to build a model that can predict annoyance at larger distances from the airports. So one of the issues is military. So we have a lot of annoyance in the province of Limburg, and there is a military airport. So that's one of the issues that has to be tackled in the future. Because, yeah, there is missing data in OpenSky. Of course, I would like to be able to go further back in time. So can we get to more historical data before 2016? Is there a way to get some information about military aircrafts, because they can be very annoying? And we have to make a rigid link between aircraft type and its noise classification in the noise database, which is not available. That's not an attribute in the OpenSky aircraft tables. That might be interesting in the future. And of course, we want to detect trends over time, and we want to check if what I do with my measurements would result in a worldwide valid model. So acknowledgements, this is a really spare time project. I use available data to its limits. That's what I do in my own time. And I suggested this as a region-wide indicator for the Flemish government, so we'll see what happens next. So the concept is definitely valid. Noise event detection with low frequency detector is very successful. Flight correlation is relatively easy if you take the physics of sound propagation into account. And I'm growing that aircraft event database now. And I'm on the lookout for projects and applications. So thank you very much. And the floor is open for questions.